Okay, so thank you very much. Thank you very much for attending this talk. There's a lot of people here. It's really amazing. My name is Sebastian Schinzel. I have a few words about me on the next slide. So my life is actually split in two pieces. So there's an academic part and there's a professional part. For the academic part, well, I'm right now doing my PhD thesis at the Security Research Group in Erlangen with Felix Freiling. And I have to say that I handed in my PhD thesis last week, so that is a very good reason to celebrate. Thank you very much. Okay, the second thing of my life is my professional work at Virtual Forge, where I do SAP security, and SAP has this strange language called ABAP, and I did certain things to this, and also static code analysis, penetration testing. Okay, so who of you did ever do any penetration testing? Can you raise your hand, please? Okay, so maybe you have seen this movie. A friend of mine, he came to me and told me, okay, I have seen this movie, Swordfish, and it was so cool because penetration testing, you do penetration testing, right? And I said, yes. And he was like, okay, penetration testing is really so cool because you can break in such a short time in arbitrary military systems, and there are guns involved, and it's so awesome, right? So, yeah, and you have young women doing strange things to you, right? Right while you're penetration testing. And, well, right, okay, so you may or may not agree. In my experience, that's not the case. There's no guns and usually no women involved in this. And it also takes considerably more time than 60 seconds to break into a system. Sometimes it works, but it's really, really seldom. Right, so that's the movies. That's how Hollywood thinks penetration testing works. But in reality, it's a bit different, right? So actually, I mean, penetration testing is split in 5 different pieces. You have preparation, and then you start gathering some information on your target system. You evaluate this information, and then you do the actually 60 seconds part where you do the exploitation and the testing and stuff like this, right? Okay, what I show today is a little bit of testing, a little bit of exploitation, but more gathering information. Okay, so when you see this talk, you will see that using side channel attacks, and a timing channel is a side channel, using side channel attacks, you can gain important information that you can use in other exploits. So, right, so you may be able to take over a system, not because of the side channel attack, but because the side channel attack gave you information that was necessary for some other attack. Okay, so that's the Pentagon. Right? That's the Ministry of US Foreign Affairs. And well, what do you need to do in order to know when the next big attack will happen? Right? So when they will attack Iran, let's put it this way, right? So usually people would say, okay, you have to infiltrate the Pentagon, you have to smuggle people in there, and they have to hide very well, and it takes a lot of preparation. And it turns out that it's not really that necessary, because when the Pentagon, just before the Pentagon, 2 days before the Pentagon does a large attack, they order pizza, an unusual high amount of pizza. Right, and so there's this article of Time magazine where they interviewed someone from Domino's Pizza. Right, so there's a Domino's Pizza in the near of the Pentagon, and he is saying that he realizes that the Pentagon is planning something because the pizza orders are rising. And this is really strange, isn't it? Because we just said, okay, it's really a lot of effort to smuggle someone into the Pentagon, but in many cases, the straightforward attack is not necessary, right? You can also try to find some other information that you can easily retrieve and that correlates with this secret information, okay? And this is what side channels are about. Side channels are often they're not really difficult to attack, or they may not be difficult to attack, but it's finding some information that correlates with a secret is quite challenging, right? So, okay. So you guys have done penetration testing, and what you do there is usually you do invasive attacks, okay? And what's an invasive attack? So you have usually the original control flow of an application that you're about to attack, And when you do an invasive attack, and that could be a buffer overrun, SQL injection, format string injection, cross-site scripting, and things like that, what you do there is you create your own control flow in this particular application. Right? So let's say this here, if this were a web browser, then you can make, using a buffer overrun, you can transform a web browser into a web server, if you want. Right? You can do this. With side channel attacks, it's a bit different. Right? So you don't actually attack the system, you use it as the designers intended their usage. Okay? So you stick with the original control flow of everything. You don't send any rogue requests to this to the application. So there are no special characters or things like that. You really just send normal requests to a particular application that you want to attack. Okay. And this is one example. This is, I would say, it's the opposite side channel of a timing side channel. I call these a storage side channel. And what you see here on the left side and on the right side, there are two HTTP headers. And both HTTP headers are from exactly the same system and from exactly the same page, because this is the login page of a typo3 backend. Okay? And what I did there is, on the left side, I used a non-existing user and a wrong password and tried to log on. Obviously, there comes some error, username or password wrong. On the right side, I did exactly the same with an existing username, and this is what happened, right? So you have two different HTTP headers, even though the content, the HTML content, is exactly the same. And this is really strange, isn't it? So from this, you can learn from any typo3 on this world, you can learn whether a username is a registered administrative user or not. And this is really quite strange, right? So usually penetration testers don't look at this. They look at the HTML, at the generated HTML, and if there are no differences, then they say, okay, that's okay. Okay, but what we want to talk about in this talk is here we talk about timing side channels, and that's a different thing, right? Take this application that does this. Okay, you start at the top. Right? So you issue a username and a password, and this is what happens in the backend. So usually it checks, does the user exist? And if the user doesn't exist, you immediately get an error page. Then there's a second check that they look whether a user is logged or not. If the user is logged, again you get the error page. Then you look, is the username expired? If yes, then again you get the error page. And then we look at the password. Right? Then we look whether the password is correct. And if you look at this, there we have the first control flow, which is rather short. And then there is a second control flow, which is much longer. Right? And even if you think further, you don't have only this one here, not only this control flow, but you have two additional ones. So you can not only find out whether a username exists, you can also find out, is he logged, is it expired, and things like that. Okay? So this example may or may not be security relevant, right? So there are systems on the internet where this would be security relevant. There are others where this is not relevant. I just use this as an example, right? So you can use any control flow that you can measure through this. Okay, so much for the theory, right? So we just you would think the first control flow has exactly one response time, and the second one has also exactly one response time. It turns out in reality that's not the case, unfortunately, because the problem is when we do measurements over a network or on a multi-user system, you always have jitter, right? Because things are busy, the system is busy, the routers are busy, there are saturated links on the way where you do the measurement and things like that. So what you can only measure, what you want to measure is the response time t. But what you can only measure is t plus the jitter that you get. And I think it really boils down, this is the target of this whole talk, to enable you, to show you certain things, how to remove this jitter from this timing. Okay. Now that's an histogram that you see here. On the x-axis, you have the response time, and on the y-axis, you have the amount of measurements that were at this particular response time. Okay, so what I did here is I did several measurements here, and that's the graph that appeared. So there are, what you see here, this is not zero, but there are some measurements which had this particular value, and there are a lot of measurements right here. Okay, and when we do a timing attack, right, this doesn't tell us anything because we just did some measurements. What we need to do is we need to compare this particular measurement with something else, right? So we use a different secret, this could be a different username, and try to compare it, okay? And this is what we might get, two different distributions. And when you look at this area here, when we get a measurement in this area, we don't really know to which it belongs. Was it an existing username or was it a non-existing username? Because for both it is possible, right? So there's a lot of overlap in the timing measurements. Okay, that's why I came up. I want to show you a few do's and don'ts of timing measurements. Okay, because what you want to do is you want to achieve timing precision, right? So you want to measure as exact as it is possible, okay? There's a paper which is in the reference from Scott Crosby, and he claims that you can measure even down to a few hundred nanoseconds over a network, over a busy network, right? So when you do the right thing, but obviously this guy is an academic guy, so he did millions over millions of measurements, right, and compared these, and that was the best result that he could achieve. What we want to do is, we're penetration testers. We have limited amounts of time. We want to go to a customer and do a penetration test against the system and, well, see whether it's vulnerable or not. Okay. So first of all, what we want to use a very fine-grained timer. And there's a certain things that you can use as a timer. This is just one of it. There's an assembler instruction called RDTSC, and that's the source code, the C source code that you could use to take this. Okay, so what does it do, RDTSC? It gives you the amount of CPU ticks that appeared during or after boot up, right? So it's very, very fine-grained, okay? And here we have how fine-grained it is. So if this computer were a 2 gigahertz machine, then you get a resolution of half a nanosecond. So this is very exact. You can get very exact timings. So it's very good because the faster your CPU is, the better you can measure. But it's also a problem because the timings are tied to the CPU clock speed. So there's a problem as soon as you have power management enabled, right? So when you have power management enabled, your CPU might decide that right now it's idle, and therefore I reduce my frequency. And when this happens during your timing measurements, all of a sudden you get a gap, you get a jump, right? And this may really severely mess up your measurements. What you also want to do is you want to parallelize measurements. So that's the naive measurement approach. That's not the parallel, but it's more like in a row, where you do the measurements in a row. So first of all, you start and measure one data set. I call this A, right? And you do the measurements of A. That could be an existing username. So you make 100 requests with an existing username. And then you make the second data set, where you take, again, 100 measurements with a non-existing username, and then you try to compare them. And the problem here is that the jitter that was added to both of the measurement sets may have changed between both, right? So we will see this later on. Jitter is also a very temporal thing. So you may have, at this particular second, you may have jitter of 5 milliseconds, and a minute later it may be 2 milliseconds. Therefore, it's much better when you measure alternatingly, right? So you take an existing username, do one measurement. Then you take a non-existing username, take another measurement, and so on and so forth. And the good thing there is that the changes in a jitter over time affect both data sets approximately the same. Okay, so we have the same effects in both data sets, approximately. So that's much better when you do this. Then a different thing is you need to decide where you start the measurement, and you need to decide where to stop the measurement. Okay? I have drawn this here. So on the left-hand side, you see there's the sender, and on the right-hand side there's the receiver. And the further down we get, the later it is, right? So the y-axis is actually the time. There's a block at the bottom, at the very top, and that's the request. And there you see a request is not a single packet where you send something out and it comes back in, but it may be several TCP/IP packets that go back and forth. And you have the same for the response, right? So you receive the first packet of the response, then a second, then a third, and there are acknowledgement packages going back and forth. And the problem is with each and every round trip, you add the jitter to it. Okay, so if you have 10 round trips, you also have the jitter of 10 round trips. So you want to reduce the amount of round trips that you do. And there are three different ways that I have detected what you can use, that you can use as a starting and as an endpoint. So there's, first of all, at the very outer part, there's the naive approach. Then there's an approach that I call when you use blocking sockets. I'll go deeper in this on the next slide. And per packet timings. Okay, let's look at it at more detail. So that's the naive approach. You start the timer, you take your request, send it over, and then you receive the response, right? And when you have fully received the response, you stop the timer. That's a very naive approach. We can make this a little better because in most operating systems you have blocking sockets. And that means I can do the following. I send n-1 bytes of that particular request and wait until it's finished. Then I start the timer, and then I send the very last byte of this particular request. In most cases, this will result in just one TCP packet with 1 byte payload. Okay? You have already started the timer, then you receive the full response, and then you stop the timer. Okay, you may ask yourself, why don't you start here when you receive the first packet? Well, the reason for this is when you have, let's say you have Apache, web server Apache, and you send over this request to the Apache, and then the PHP application, let it be a PHP application. While this PHP application is running, Apache may decide to already send the response headers asynchronously. Okay, and if you measure this, you don't get the actual PHP application, but you get the amount of time that it took the Apache to send the response header. Right. So okay. And then there's the last one. Again, you start at the very last byte in the request. And then if there were a way to know which particular packet denotes the first packet of the real response, of the PHP response, right? Then we want to measure there. That would be the best approach. Because then you have reduced the amount of round trips that go back and forth, and therefore you have reduced the jitter. Okay, so and there are some further tips. So first, yeah, that's what I already said. Disable the power management. That you can do on Linux very easily. Measure over the wire. So right, so don't use Wi-Fi, because when you do Wi-Fi, it may happen that some other machine is doing some measurement, and then your packets get dropped and things like that, because it's just a collision domain, right? Do everything to reduce any disturbances on your local machine. So that means any periodic tasks or so. Disable your email program and things like that. Okay, and also try to keep your part of the network idle. So if you have your home network, a DSL or so, you should shut down the file sharing for the time being, and then start your measurement, and then do the file sharing later on. Okay. Right, and that's what I added 2 hours ago. Don't do it from hacker conferences, because the network quality is very, very weird. But we're going to see this later on. Okay, and then the last one is the first few dozen or the first 100 measurements contain much more jitter because of all the caches that warm up during your measurements. Right, so there are caches on your local machine, there are caches on the distant server, on the routers, and so on. So that means basically throw away the first measurements, right, and use the later ones. Okay. Before I continue, what I want to do is because it reminded me to start the actual demo. Okay, let's continue. Okay, so what I want to share with you and the penetration testing community are two different programs. The first one is a programming library which is written in C. We call it FAU Timer. FAU is Friedrich Alexander University, the Erlangen University. The reason that we have written this in C is because there we can use inline assembler, because we use the RDTSC assembler thing. We ported this to Python, so that's what I have already here with me. And it encapsulates the logic for the timing measurement. And if you look at this, this is what you usually do. So right at the top, you have a timing attack script. And this timing attack script calls some network sockets and does all the timing measurement by himself. Right? And what we do here is we use this library just as an intermediate part. Okay? So in your timing attack script, you need to generate a request, and you pass this over to FAU Timer, and it will do all the sending back and forth for you, and it will also do the timing measurement for you. Right? So you don't have to deal with network sockets, and you don't have to deal with a timing measurement. Okay. So let's have a look at this. I've written a very small hello world. Okay, so at the very top, you see there's a request. That's a very simple HTTP request. That's the one that we are going to send to the server. And here we just have a loop. We do some initialization to this library. Here we send the request, and this is where all the magic happens. Okay, this is where we do everything. And right here at the bottom, we just get all the things that we require from the library. So at this particular point, everything was done already. Okay, so we get the CPU speed. So our library is capable of determining how fast this particular CPU runs. We get the ticks, we get the time, and we can also get the actual response from this. And if I let this run, this is pretty much how it looks like. Okay, so it does everything for you. You can just use this for your attack scripts while penetration testing, and just use this library, and it does everything that is related to measurement and socket handling and so on. Okay, what I need to say here is my both student helpers helped me a lot doing this, so that would be Isabel Schmidt and Nils Ichik. Thank you very much, guys, for this. Okay, now we're at a point where we can do measurements, right? So we do the best that we can to produce a data set that has as little jitter as any possible. Okay, now but then we have just a comma-separated value file with all the timings in there, and now we need to do some analysis, right? So there are tools, right, to do this analysis, and basically what we're doing here is statistics. Right? So you can use any statistics program that you want. That would be Gnuplot, MATLAB, Stata, R, or just your favorite spreadsheet. So you can use OpenOffice, Excel, and so on and so forth. Right? And there, when you use these tools, you can display the data that you have just measured in various plot styles. So for example, there's the classical scatter plot. We will see this in the next slide, how they look like. And there, you can detect temporal disturbances. So let's assume that the link quality dropped intermediately at some certain point, right? Or we also see very good the overall quality of measurements. Then we have a box plot, and there we have several values graphically tied together. So there would be the median, for example, the minimum of the measurements, the maximum of the measurements, and so on and so forth. And then we also have a histogram, or a cumulative distribution function, a CDF, and there we can compare the distributions of these data, right? Okay, let's have a look. Okay, that's a scatter plot, and this is a scatter plot that I did in my home network. I did this in a university, and what you first see there is there are no obvious timing differences, right? So I zoomed in here, and it doesn't really look that different, okay? But it's also, I have to say that a scatter plot is not very good in determining differences. But what we see here, we have a lot of outliers, right? So we have outliers to the top, and we have also outliers to the bottom. And those very low outliers, they are really strange, because I would assume if, let's say, a certain process takes a certain amount of time, and I add jitter to this, then I can only add jitter. Right? So when I have a process that takes 2 milliseconds to finish, and I get jitter on this, then all of a sudden it can't be 1 millisecond. It has to be higher. But what we have here is we have outliers at the very bottom. So that's very strange. But you see this in all network measurements. You see these guys. And also what you see here is where things were messed up in a way, right? So here's a jump, right? All of a sudden here, all the measurements took considerably longer time, and here they are smaller, smaller, smaller. So this may be a case of a timing data set that is not very good. I thought this one was not very good until I came to this Congress. Oh, sorry, animation takes some time. Okay. So that was 2 hours ago. I was sitting in a speaker's room, and I looked at the dashboard of this Congress, and they told me 18% and 5%. And then I did a demo scan, and I saw this, right? Okay, so there's so many outliers, right? So you see a cloud of measurements. You see them here. You see another cloud of measurements here, and you see another cloud of measurements here. This doesn't make any sense, right? So this data set is unusable for timing attacks. What you could do, if this is the best that you can, is you could filter out these ones. So it could take this cloud, only the measurements in this cloud, or better, only the measurements in this cloud, and do a comparison on this. It's worth a try, but I wouldn't go so far. I would, if you see this, try to repeat the measurement from a different network, for example. Okay, so I'm really not so sure about that. It looks much more saturated to me, the network. Okay, then we have a whisker diagram, and a whisker diagram shows us certain things. So first of all, the fine line in the middle is the median, the 50% percentile. And 50% percentile means that 50% of all the measurements that we have in the data set are below this line, and 50%, the other 50% are above this line. Okay, then we have the upper quartile. This is the 75th percentile, and also we have a lower quartile, and there it works just the same, right? So for the lower quartile, we know that 55% of all the measurements are below this, and 75% are above this, okay? I haven't shown the 25%. And then we have the cumulative distribution function, and you read this as such. So this here is a probability, and this here is a time, the x-axis. And what we see here, this is approximately 75%, because that's a probability. And when we put the line down here, we see we are at this particular value, and then we know that 75% of this are below this particular value. This is just so that you know how to read this particular graph. If you had a uniform distribution, it would be a line, a diagonal line. Okay, so what can we see here? If we zoom in, then we see where these two functions are not perfectly overlapping, and those are the ones that we are looking at. Okay, so if you look at the green line, you see certain red spots, and that is the red function luring behind the green one. And those are the parts where we can distinguish both data sets. This is the ones that we are looking for. Okay. what we have did right now was to show it graphically, right? To take our data set and make graphs out of it. There are algorithms where you can do this as well. So there's, for example, the student's t-test or the Wilcoxon test. Those are two tests, hypothesis tests, that will tell you if two data sets are significantly different or not. Okay? And again, Crosby, in this paper that I already mentioned, he tried out both of these, and he found that they don't really work very well for a timing attack because there are too many false negatives and too many false positives. And therefore, he came up with his own test, which I don't want to describe in detail, but we're planning to include this in a second tool that I'm going to release today later on. So this is work in progress. We know how to build a very good algorithm to compare these on an automatically way, but it's not yet implemented. And I do a demo on this in a few slides. Okay? But let's get over for the attacks. Okay? The attack that I want to show you was we want to guess a username at a typo 3 backend, again, the one with the different HTTP headers. But this time we don't look at the HTTP headers, we want to look at the response times. Okay, how do you do this? So first of all, you have the username in question. So we want to know whether admin exists, whether this is an existing username. But we need to compare it to something else. So either you know one existing username, or you choose a username which doesn't exist with very high probability. Right? So you can randomly generate a username and use this as a username which does not exist. And then you compare both the measurements. And we also have an hypothesis here. We say the login requests with admin take measurably longer than those with something else. Right? So I use this particular number, and I assume that it doesn't exist. It doesn't exist. Okay. Let's see how many we have. Okay, so we so far have only 500 measurements, and I think that the data set that we get from this will be very bad. So I tried several from this particular network here, and they all look very bad. But we try it anyway. Okay. Oh yeah. Okay, so the reason for this is that this is not yet finished. I'll quit this and have a look at the oh man. That looks good. Okay. Fingers crossed. There we go. Okay, and so what this tool really does is it's a reporting tool. So all the graphs that I have shown you on this on the slides were generated by exactly this program. Okay, so what we are releasing, we're going to release these two tools in January. The first is there for you to produce measurements, to produce a data set, and the second one is a tool to generate plots from this particular measurement data set. Okay. Now let's have a look. Okay, it generates a PDF report. Right? Oh yeah, a lot of ads in there. Sure. Okay, so there's a bit of text where I can explain, where I explain exactly the same things that I've just explained to you, what these particular plots are for. Let's scroll down, and you see again, okay, this data set is really messed up. Right. So again, we have this strange clustering here. We have 3 clusters here. The first, the second, and the third. Well, let's look at it a bit deeper. Okay, so we would think that the red thing here should be higher in general than this particular thing. And if you look at the lower quartile, it really looks different. But here the median doesn't look that different. So let's look further. Yeah. Here you see the different clouds, right? So we have these different bows in here because the data set is really not good. Okay, and in a second chapter, what we did there, we applied a filter. So we do some filtering in this tool, and we try to reduce this data set in a certain way that only those measurements are included and are displayed that show the most information to our knowledge. Okay, so that's a scatter plot. We don't see much. And here we see a thing that we wouldn't expect. So admin is actually lower than the other one. So this data set is really not good, right? Here, this is exactly the opposite what we would expect. So that is the reason, right? Okay, so the data set is really bad. What I can show you is, I should have, backup report. Okay. So that's how I would expect a measurement to look like, right? So that's how it's supposed to look, and this is done on an ordinary DSL connection that was idle. So I did this at home, so you don't need any fancy links, right? So I would even expect if I would do the measurements in with a UMTS connection, it would be much better than the network in here, right? So that's just the case. Sorry. Okay, here we see already the differences. Median is very different. And we go down to the filtered ones. Right, and this is how it's supposed to look. So that's the reduced data set, right? And there you see there's a significant timing difference. And this is also how it's supposed to look, right? And from this one, this is a step which I can't show you because of the time pressure that we have in this talk. You could use the values that you have learned from these graphs in order to make a real script and to do a brute force attack to find out whether username exists or not. This you can do with this information. Okay. There's a second example, and this example I've taken from an existing paper, which was already published, not by me, by other people, but I tried this by myself. So what we want to do here is we want to know whether private pictures are included in an album of an online gallery. Okay, so the thing is, let's say you have a gallery and it only shows 5 pictures, but I want to know whether there are more hidden pictures in the back end. And this is really what we got. So we created a lot of albums, and all those albums only showed a single picture to anonymous users. Right? So down here we have the different albums, so the albums are numbered, and here we have the microseconds. And this is not, I have not drawn this by hand, but this is really how the filtered data set looks like. So you can tell, for example, this particular album here has 10 hidden pictures in it, and this particular one here has 30 hidden pictures in it. There's a lot of things that you can do with these timing measurements. Also a difference here compared to the typo 3 example. With the typo 3 example, you have a binary result. So does a username exist or not? And in this particular case, we don't have a binary thing. We have more like an amount of things. And we can do this using timing as well. Okay, those were the known attacks, and now we have what we call a 0-day even. It's even a 0-day. Oh my gosh, come on. Okay, so this is there's a standard out there, and it's called XML encryption. Well, this is the whole thing that I'm showing you right now is joint work with Juraj Somorowski and Tibor Jager. So what is XML encryption? Okay, so with XML encryption, you take subtrees of an XML document and encrypt this and paste it again in the XML document and send it over some line. Okay. In this case, we have 2 blobs here. It's a hybrid encryption that they use there. So they use a session key, which is encrypted with RSA. That's this one. That's the session key. It's RSA encrypted and included in here, and that's the actual data. So this is the encrypted subtree of the XML document that was pasted in there. Okay, how does the decryption of XML messages work? So first of all, you take this cipher data and RSA decrypt it, right? Because you want to have the session key. In the second step, you return an error if this session key does not comply with PKCS1. We see later on what this is exactly is. It's in a coding format. Else, if there was no error, if it does comply with PKCS1, we decrypt C data over here. Oh, sorry, wrong button. We decrypt C data, that is this one. We copy the subtree that we have just decrypted again back to the XML document. Then we pass the XML document and we return an error if the XML was not valid. And that means we have a timing difference, and through this timing difference we can determine whether this is PKCS1 encoded or not, this particular part. That's the first puzzle piece of our attack. Now comes the second one. In 1998, there was a guy called Daniel Bleichenbacher, and he showed in his paper that you can break RSA within 1 million requests using an adaptive chosen ciphertext attack under the condition that you get an oracle. And this oracle does nothing more than tell you whether a certain ciphertext was PKCS1 compliant or not. So that's an algorithm, right? And you don't have to understand the math of this, right? It's really just important to know that when you have RSA encryption and someone gives you an oracle that tells you whether or not a given ciphertext is PKCS1 encoded or not, then you can break the whole RSA, right? So you get exactly the clear text out of this. So that's the second puzzle piece, right? I just said in XML encryption, in this standard, the way that it works, we can determine from the amount of time that it takes to process an XML encryption message, we can learn whether it's PKCS compliant or not. And here we have an algorithm that allows us to decrypt it, given the fact that we have this oracle. Okay, how do you know whether something is PKCS1 conformant? This here is how it looks like. Okay, so you have this, you have an RSA encrypted session key, and it always starts with a 002, always. Then you have some padding, then you have a 0 byte, and here comes the data block. This is the session key. And what most implementations of XML encryption do is they check whether this starts with 0002. Okay? Now, and this is what we have done. Okay. I already told you that this one here will only be decrypted if this key that is included here is PKCS1 compliant. And here we can fill in anything, right? Because the attacker can change this. So I can include here a megabyte of data, and this megabyte of data will be decrypted. It doesn't have to decrypt to something meaningful. It just decrypts it. That's all that we need, right? So this is only decrypted if this is PKCS compliant, and the size of this information here, of this data blob, can be set by the attacker. And this is what we did here. So what you see here is the size of this particular block. So here we have 100 kilobytes, here we have 1 megabyte, and here you see the milliseconds. And there, for this, we get two different graphs. So the lower one, where the decryption does not start, it's this one. And the higher one, where the decryption starts, which is PKCS compliant, is the upper one. So we have a significant timing difference, and thus we can use this to decrypt XML encrypted messages. Okay, how did we do this? How did we do the attack? First of all, we split our attack into two phases. So we have a learning phase and an attack phase. And then we start measuring the response time of a PKCS1 compliant measurement. Then we get this. That's a cloud of measurements. Then we take the lowest one. So we find the minimum response time and call it just a PKCS1 compliance boundary. Okay? And now that's a question for you. If I get a measurement here, what does this tell me? It's not compliant, correct. Okay, so any measurement below this boundary definitely is not PKCS compliant because the decryption didn't start, right? It didn't start. What happens if I have a measurement here? Sorry? You can't know. That's exactly the case. So when you are here, it is above the compliance boundary, but it could be two cases. There are two cases what we could measure here. First of all, it could be a compliant measurement that would be here, but because of the measurement jitter, it would be above here. Or the second case could be it's not compliant and we have high jitter. Okay? And in this case, what we do, if we have a measurement above this boundary, we repeat the measurements n times. Let's say we repeat it 50 times. And if after 50 times all of them were above this, we know it's PKCOS1 compliant. The good thing about this, I told you this attack takes around 1 million attacks. Most of them are not PKCS compliant. Right? So we don't have to repeat this very often. And that's the actual attack that we did on a local host server. Right? So here we used 100 kilobytes of data that we sent over this. Here we have this boundary that I just told you. The upper one are the PKCS1 compliant measurements, and the below one are those that are not compliant. And using this, we could decrypt the ciphertext within 3 hours on this laptop. So very fast, actually. Yeah, I already said it's 100 kilobytes of C data. It took us a little more than 300,000 Oracle queries, but this really depends on the particular RSA key that we used. So it could be above 1 million also. It really depends on the RSA key. But what is really interesting here is we just needed, on average, 1.24 requests per Oracle request. And that's very fast. That's a very fast timing attack. Now you could say that's localhost. We tried the same on an internet server. And what we did there is we increased the size of data that's supposed to be decrypted to 1 megabyte, so that the timing gap gets bigger. Okay? And there we could decrypt the ciphertext in less than a week, right? And we also took only 1.2 requests per Oracle query. Right? So that's a feasible attack, also a timing attack over the internet, which works quite well. Okay, one of my last slides. What time do we have? How much? 10 minutes left. Okay. So, okay, this all is work in progress. So even when I finish my PhD, I really want to continue on this. And that's a call for participation. So there's many open things in this. Right? So these two programs that we are about to release in January, they do very basic stuff. They do the right things, but they can be improved. And there I need students who are looking for master thesis, diploma thesis, bachelor thesis. If you are an open source hacker and want to contribute, you can do this here. Just drop me a line. Oh, and what I also wanted to say, I'll release the URL of the two programs on Twitter somewhere in January. So my Twitter is here. Okay, yeah, there's some literature and further reading. Right? If you're interested really in this, you can look also on these. And that's about it. Thank you very much.
If you must leave now, then please do, but quietly, until the Q&A session is over. So if you have any questions, raise your hand. We have a second microphone over there. We'll try to get to you and let you ask the question. Okay.
Hello. In the last in your last try test, you say you needed a week for decrypt the XML. What connection you had in that test?
Okay, so that was a university connection, right? So it's quite fast. I would say 100 megabit. I would say, right? The reason that it was 1 week was because we do have to transfer a lot of traffic. So it's really a lot of gigabytes that we have to send back and forth in order to do the attack. And from the jitter and things like that, it wasn't particularly well. But what we needed is a big uplink. So we needed to send a lot of data, and that's why we did it on the university. But you could do it in theory also with your DSL link. Would be sufficient. I think there was someone.
In terms of preventing these kind of attacks on my code, the first thing I'm going to do when I get home is add some random sleep statements to my authentication routines. But is there anything else that you can suggest that might be a bit cleverer than that, maybe?
Okay, that's a very good question. I have prepared a few slides to this. And I'm very glad that you're asking, because this is really also the interesting part. What can you do about it? And I can tell you, it's an own talk. So I would need an own speaker slot to really talk about this in general. But what you want to do, actually, what you just said was a random sleep, right? So in the first step, you get a random number, and then you do some modulus on this, because you want to prune this to a certain maximum sleep statement, right? And what we did here is 200 microseconds, and then we did this sleep, okay? And we did this with this data. I hope you guys can see this in the back. So that's the initial data set that we see here, okay? And then we produced a data set, filtered this data set, and this is what resulted from this. So what you see here is actually now this line here, and what you see here is this line now. And you see it's more edgy, it's more noisy, but it's still significant, right? So random delay padding doesn't work very well. If you have a smart filter, if you do smart filtering, you can remove this. There's a paper. What I'm doing, what I want to, so you guys have to, you have to promise me that you tell no one, right, about this, okay? So there's a thing which is actually provably secure, right? This is part of my PhD thesis, and it's very easy. It's actually very easy. Okay, let's take the part where you have an existing username and a non-existing username, okay? The existing username or the non-existing username is this input here. That's the username in a string. Then you append some secret to it, and this secret has to be static. And the attacker must not know it. And then you do some hashing on it so that you get a number which looks random, but it's deterministic. Because for the same input, this will always produce the same measuring, right? And then you do, again, the modulus to it, and then you sleep on it. And when you do exactly the same, so that's the same data set as I have shown you, and the same good filtering that I did, you get something like this. So that seems to be much better. And there are other ways as well what you can do there, right? And this is only, I mean, these things that I've shown you here are only those things where you can't influence the timing differences. What I want to show you is, I also have a slide for preventing exactly the attack that we have against the XML encryption. And the problem, the vulnerability sits exactly here, because we return an error if it does not comply with PKCS1. And the fix to this, and that's an implementation fix, not a fix to the standard, is we generate a random session key, right? And if it does not comply with PKCS1, and then continue, right? So we decrypt the data at the bottom, with some arbitrary key which generates rubbish, right? That's not XML, but the good thing is that it's not XML. He will only learn in step 6, so we have no timing differences anymore. Okay. I'm sorry? Yeah, okay, so the question was that generating a random key does take time. That's true, but what we could do is we could generate the random key here as well, right? And then we just have this single assignment, and you can't really measure a single assignment. I wouldn't say this is feasible.
Well, as a responsible admin, I would obviously monitor the network traffic for suspicious IPs who try to send gigabytes of data within 1 week or a couple of hours, and obviously filter out the first wave this way. Especially for Planet Lab, I mean, you said you basically DDoS them to a certain degree. Didn't they catch you in some way?
Okay, so I mean, what we did is when we did the measurement on Planet Lab, we didn't run it all the way through. And the reason for this is we have implemented the Bleichenbacher attack, right? And we know exactly at which particular step a PKCS1 compliant key comes out and when not. And we tried this just for, let's say, 10,000 measurements. And as we had exactly the same signature, right, the same sequence of compliant and non-compliant keys, therefore we inferred that the oracle is working, right? The next thing is, I see this attack very relevant on, let's say, for example, on the Amazon cloud, right? So let's say you have you have rented a Linux server on the Amazon cloud, and there's a paper which shows what I need to do to be co-located on the Amazon cloud on your particular. So to be co-located on the same hardware as your VM, and then I do this localhost attack, and there's no monitoring, right? So there I can send arbitrary amounts of data on the local host, and nobody will look at this. Okay.
Isn't the bug fix essentially a way to do a denial of service against yourself? Because in case the attacker guesses the random the session key incorrectly, you can abort earlier. Well, either you have the oracle function and return early, or you decrypt everything and the attacker can throw arbitrary amounts of data at you without guessing anything correctly, and you just waste CPU cycles in a big way.
Mm-hmm. I'm not sure whether I have really understood it. So you were saying the attacker is changing the data. It's changing the data that he sends to us. And what?
The idea was that the fix, which is suggesting, does eliminate the shortcut which you could use otherwise to reduce the amount of data you have to process. Mm-hmm. So the attacker doesn't have to care anymore to give you some, if he just wants to do a denial of service and doesn't want to break in, he can just abuse this mitigation technique to overload your CPU more easily.
Okay. I think I know what you mean. You're saying that if the attacker sends arbitrary stuff to my server and the server has to decrypt it and so on, he can do this anyway. The reason for this is when he eavesdrop on one XML encrypted message, the one that he wants to break, he already has a key that is PKCS1 compliant. So this makes him, he's able to actually use the key that he wants to break and send it with some stuff to the server, and the server will decrypt it, also in the vulnerable case. So he can do this already, but it's a valid attack. I mean, you're right. Any more questions?
I would like to know, so your tool, how low can it measure? So for example, if you make an attack local network, if you make an attack on the internet, and like you said on Amazon, so what can you measure? You can measure microseconds, how many, and this kind of stuff.
Okay, so I have been down to a few microseconds on the internet, but this is so the what you can do always is let's put it this way: if you have a timing gap that is very low, right? What you can do is you measure a lot of times. Well, let me give you an example. If you have 10 milliseconds, you can measure this with five requests. That's enough in order to cancel out the jitter. If you have a timing leak of 5 microseconds, you may have to measure 1 million times, even more, right? So that is. There's no hard boundary of what you can measure and what you can't measure. It's more like a question of feasibility, right? It doesn't make any sense to send billions of requests and to wait 10 years for this. Yeah.
Have you looked at the feasibility of guessing HMAC values based on the time it takes to compare a valid HMAC with the invalid input?
Okay, no,
character by character?
No, I haven't done it, but it's on my list, right? So I really want to do this. That's a very good one, right? So what you're talking about is more like if there's a login, right, and you in the backend there's some hash comparison because the password is not stored in clear text; it's stored as a hash. And what the attacker does is he sends over a hash that starts with 0. And then then he does the same with a hash that starts with 1 and 2 and 3 and 4. And at one measurement, he sees that it takes a bit longer because the hash doesn't stop at the first comparison, but he goes to the second one. And so you can guess, yeah, you can iterate through the hash values much more easy. Yeah, I'd like to do this. I've never done it.
Okay, thank you for your... Probably yes. Yes, it was on. Thanks. Thanks for this talk. Have a round of applause.